giving me this opportunity to join this very fascinating conference. So today I'm going to talk about a photodoped effect in the Mott insulating state in term with a perspective of a theorist. And so I'm a bit simple. I'm a simple-minded theorist. So the setup would be very idealized. So, but please be patient. Yeah. So firstly, I would like to acknowledge the great collaboration with these people and also the funding from this project. Okay. So as we know, doping is an important knob to control the physical property of stronger coordinate systems. So for example, please imagine the Harvard model. And as we know, if this model at the half-filling condition and when the Coulomb interaction is large, electron cannot move from this kind of single occupied configuration, and the system becomes a Mott insulator. And you can add some charge carriers into this system, for example, by doing chemical doping, and this actually leads to an emergence of the various correlations, which leads to an intriguing phase diagram. And on the other hand, non-equilibrium setup allow us to do this kind of doping, but in a different way. So let's imagine this initial Mott insulating phase. Now we think of exciting this system using some laser across the Mott gap. Now we have the situation where the system have a non-occupied side horon and double occupied side doublons. So they are the two different types of charge carriers. So the crucial difference from the previous equilibrium case is that now we have two different type of carriers instead of one, unlike in the equilibrium case. And this kind of difference may lead to an emergence of an intriguing phase that is absent in equilibrium. Yeah. So actually, these photoexcited carriers starts to have a very long lifetime. If the system have the large U, or the gap becomes very large. And in such a situation, in the relaxation process, this number of photocarriers are approximately conserved. So what happens in the initial stage is that the relaxation within each band of the upper and lower Hilbert band, and also the cooling of the charge carriers due to the potential coupling with an external environment. And this leads to an quasi-metastable state or relatively long-lived quasi-steady state. Yeah. Now the question is, what kind of phases are expected in this kind of quasi-steady state regime of the photodoped large gap Mott insulator? There are several options to study this problem. So the most obvious one is to do the direct time evolution of this kind of photodoping processing, starting from the real time excitation using some numerical techniques. Yeah. However, this kind of direct approach is often numerically expensive, and it's hard to make a systematic analysis. And the second idea is to approximate this quasi-steady state as a true steady state, which is stabilized by attaching external bath to keep the number of photocarriers. And they're similar, but the third idea is to approximate this quasi-steady state as some sort of equilibrium state that is defined by the fixed number of the photocarriers. And this idea is analogous to what has been done in the context of photodoped semiconductors, and actually what we are going to mainly focus on in this talk. So by the way, if you are interested in this general photo-induced dynamics of the Mott insulator, I wish to refer to this paper about review paper from a theoretical point of view. Okay, so I want to introduce this quasi-equilibrium approach for the stronger this system, but to do this, let me first remind you of the case in the semiconductors. So in the case of semiconductor, you excite the system. Now we have a hole and electron in the conduction band and valence band. And again, these charge carriers have relatively long lifetime, and so what happens initially is a relaxation within the band, and the system approaches some quasi-steady state. Now, people has been treating this state with some equilibrium state, which is characterized by the separate chemical potential for the conduction band and the valence band, and also introduce some effective temperature. So people analyze this effective equilibrium problem to write down the non-equilibrium phase diagram of the photodoped semiconductors. So we want to use this kind of idea to the stronger equal system as well. A bit of issue here is that this doublon and holon, in the original Harvard language, doublon and holon are not a perfectly conserved quantity. So there is always some virtual recombination and creation processes. So what actually practically conserved is the doublon and holon that is dressed with this kind of virtual recombination processes. And actually, this Schrieffer-Wolff transformation allow us to rewrite our original Hubbard Hamiltonian to an effective Hamiltonian, which is based on these dressed entities. So after saying this, the quasi-equilibrium description for the stronger equal system can be summarized as follows. So in the step 1, we apply the Schrieffer-Wolff transformation to the original Hamiltonian, Hubbard Hamiltonian, and truncate out the higher order recombination term of the charge carriers and get an effective model that exactly conserve the number of charge carriers. So in the second step, we introduce the chemical potential for each type of charge carriers, as well as the effective temperature, and regard this photodoped state as an equilibrium state that is described by the generalized Gibbs ensemble. And in the third step, we solve this practically equilibrium problem using our favorite equilibrium tool. So the good point here is that we can analyze this photodoped system systematically using some method that is developed in the context of equilibrium. We don't. Photon is it's embedded. So the photon is just an activation of the number of charge carriers. Yes, exactly. So, but that we truncate out. Yes, it's a quasi-equilibrium. Okay, so let's look at some example, which we use here. We use extended Hubbard model, which is written here, and we are going to focus on this model. So, and we assume that this local interaction is much larger compared to the hopping and also the nearest neighbor interaction. After the Schrieffer-Wolff transformation, we obtain this type of effective Hamiltonian. So at the order of hopping, we have a doublon-holon hopping, and at the order of the exchange energy, we have several terms. But in particular, these two terms are important. The first term is corresponding to the exchange coupling of spins. So it is expressed with the usual Heisenberg, antiferromagnetic Heisenberg type coupling. The second term is corresponding to the exchange coupling for the doublon and the holons. And actually, we can introduce pseudo-spin degrees of freedom for this doublon and the holon in this way, so which we call it Yeta spin. And with this, this term can be expressed with a ferromagnetic Heisenberg term. And we have here the nearest neighbor interaction, and the rest is the term that involves three-side terms. So it's something like TJ model derivation from the Hubbard model, if you are familiar with this. Okay. And so previously, in this seminal work, they studied this model in the context of the quasi-steady state, quasi-equilibrium idea. And they focused on the extreme doping case where system only hosts doublon or holon in the context of a cold atom system. Now the effective Hamiltonian is just like this ferromagnetic Heisenberg model, and they solved this system, and then found that the state is looks like this, and it is characterized by the staggered superconducting order. So actually, if you look at this state in detail, it turns out this is can be regarded as a superposition of the so-called Yang-Yeta pairing state, so which is expressed here. So, and you can see from this definition, this state can be regarded as a condensation of the Cooper pair, whose central momentum is located at pi. So usually in the equilibrium S-wave superconductor, we expect that the Cooper pair central momentum is located at 0. So in this sense, it's a special superconducting phase. So now we want to go beyond this extreme doping case to wide range of doping level and see what happens to the photodop system. So to this end, we focus on the one-dimensional system, and we analyze this effective model using numerical technique based on the tensor network and also analytical discussions. So the major findings are shortly summarized as follows. So we actually found an exact form of the wave function of the photodop system, and from this form, many interesting physics can be predicted for the photodop system. So let's look into detail. So let me start with showing the form of the wave function. So it actually represents, so we consider large U limit and think of the effectively low temperature case. And so the wave function is expressed in this way, which is factorized into 3 parts. One is spinless fermion part, spin part, and the eta spin part. I'm going to discuss what it means in a minute. But before I do that, let me remark a few stuff. So if you are familiar with 1D doped equilibrium Hubbard model, there is a spin-charge separation. And related to this, there is a well-known state called Ogata-Shiba state, which is expressed as a direct product of the spinless fermion and the spin. So compared to this, we can say that this is a natural extension of this Ogata-Shiba state to the photodoped case. And this state is representing the existence of the spin charge and also eta spin separate degrees of freedom. Okay, so now let me explain what is the meaning and how we derive this expression. So to this end, let's think of the L-site system with an S number of single occupied site and an eta number of double and holons. So firstly, we introduce a new representation of the original state. So here I show the idea schematically. So left-hand side is the original representation of a state, and the right-hand side is a new representation. So it consists of the 3-part, spinless fermion, squeezed spin, and the squeezed eta spin. So spinless fermion part is defined on the L site with an S number of particles. And this part represents the position of the single occupied site in the original representation. The squeezed spin space is defined on the NS site, which represent the configuration of spins. And the squeezed eta spin space is defined on the N eta site, and it represents the configuration of the double and holon degrees of freedom. So after this, we can proceed. And so this exact wave function form can be derived by the perturbation theory. So at the zeroth order, the effective Hamiltonian only hosts a hopping of the double and the holon. And it turns out in the new representation, it can be this leading term is expressed with a simple expression like this, which is a free spinless fermion Hamiltonian. So at this level, the ground state of this Hamiltonian can be factorized into this part, so spinless fermion part, and the random spin and the eta spin part. So this means that there is a degeneracy of the spin and the eta spin degrees of freedom, but this degeneracy can be lifted by if we consider next order contribution. So we apply the degenerate perturbation theory. So that means we make a projection of the perturbative terms at the order of the exchange energy to this degenerate subspace. And at the end of the day, we get block diagonalized Hamiltonian for the spin part and the eta spin part. So spin part is represented as a SU2 Heisenberg model with a renormalized exchange energy as a function of spin density. So, and the eta spin part is represented with the XXZ model, whose coefficient is renormalized as a function of eta spin density. And so, to summarize, we now have this kind of factorized form of the wave function. So spinless fermion part is described by the free Hamiltonian. Spin part is described by the Heisenberg Hamiltonian, and the eta spin part is described by the XXZ Hamiltonian. Okay. So actually, we can tell many stuff from this expression, but here let me focus on the non-equivalent phase diagram of the photodop system at half filling. So to this end, we focus on the eta spin sectors, which is described by the XXZ model. So as we know, we have two different types of phases in the XXZ model. So when the Jz is smaller than Jx, we have the gapless phase. And in the original electron language, this corresponds to the eta pairing phase, which is characterized by the slowly decaying staggered pair correlation. So this means that this corresponds to the condensation of the Cooper pair with the central momentum is located at pi. So on the other hand, when the Jz is larger than Jx, this is XSC model shows the gapful phase. And in this phase, in the original language, it corresponds to the CDW phase, which is characterized by the slowly decaying charge correlation. Yeah? And this state also turns out to be a special state because although the correlation decays with a power law, if you look at the squeeze space of the eta spin, it has a true long range order. So in this sense, this state is characterized by the so-called spin type order, which like in the case of Howden phase, if you're familiar with. Okay. So if we write down the resultant phase diagram in the plane of photodoping level and the nearest neighbor interaction, it looks like this. So without doping, it's in a system is in equilibrium. So we have the conventional equilibrium SDW. And with the doping, there is the emergence of the eta pairing phase and CW phase, and their phase boundary is corresponding to the SU2 point of the XXZ model. And if we do not consider the contribution from the three-side term, the boundary becomes like this. So this means that three times term is favorable for the creation of the eta pairing phase. And also this actually this phase boundary is independent of the photodoping level. Yeah. And this point is nicely reproduced by the numerical analysis based on the tensor network analysis like this. So this result indicates actually that the discussion in the large U limit works well even for the finite U cases. Okay. And so we now know the phase diagram. So we want to know what is the character of these interesting phases. Yeah. So one important quantity here is the quantity so-called central charge, the total central charge. So roughly speaking, this is some number, it's some integer or half integer, but okay, it's an integer here. But it's essentially count the number of massless mode in the system. So if you look at this form of the wave function, a spinless fermion part is described by the free Hamiltonian. So this is gapless. The spin part is described by the Heisenberg model. This is also gapless. So this already explains that in equilibrium, we have C is equal to 2, and it is the case. Okay, but in the photodop system, we have additional degrees of freedom, which is eta spin. And this part can be gapless for the eta pairing phase, and can be gapful for the CW phase. So from this, we can naively expect that, okay, we have C is equal to 3 for the eta pairing, and C is equal to 2 for the CDW. So actually, this conjecture can be numerically checked again with this tensor network ITBT method. using some scaling analysis for the entanglement entropy. I skipped the detail, but with this kind of analysis, we can get this result where we see that this central Yeta pairing phase, we have a central charge 3, I mean total 1, and CW, we have 2. So when we have this C is equal to 3, it's may a bit interesting because in the case of equilibrium, we only have C is equal to 2 at maximum. But in the photodop system, we have C equal to 3. But this is because we are inducing new degrees of freedom, which is a character type of the charge carriers into the system, and that actually leads to an intriguing property of the system. So that's one message. And okay, so this kind of discussion of the massless mode or have a direct impact on the single particle spectrum, which can be measured with a photoemission spectroscopy. So the single particle spectrum essentially measure the energy cost that is required for injecting or removing one electron to the system. And in the case of equilibrium doped system, so electron can be regarded as a combination of the charge and the spin degrees of freedom. And usually they are gapless, both are gapless. So, this spectrum, single particle spectrum, can be regarded as a convolution of these two type of excitation. And therefore, because they are both gapless, we can conclude that, okay, the single particle spectrum is also gapless around the Fermi level. So on the other hand, in the case of photodop system, one electron can be regarded as a combination of charge, spin, and Yeta spin. And former two are gapless, and for the Yeta pairing part, it is gapless for the Yeta pairing, and it's gapful for the CW phase. So we can naively expect that, okay, Yeta pairing phase, we have a gapless around the Fermi level. On the other hand, CW phase, we have a gapful around the Fermi level. And we can actually confirm this conjecture as well using numerical techniques. So here I show the integrated single particle spectrum, and this is a momentum resolved spectrum. And this blue part is the field part. And you can see that there is no gap around the Fermi level for the Yeta pairing phase. Actually, this is consistent with what has been discussed, pointed out in the DMFT analysis. And for the CW, we have evidence of the development of the gap around the Fermi levels. And with this, I wish to conclude my talk. So the take-home message is that if we think of the quasi-steady state, which appears in the large gap photodop system, there is additional degrees of freedom, and this can lead to an intriguing physics. And the quasi-steady state approach is one technique to make a systematic analysis to this kind of problem. And thank you very much.